If you build a physical machine, it will eventually break down. Friction, moisture, and temperature fluctuations constantly attack materials, wearing them down over time. This life cycle is mapped using the bathtub curve, plotting failure rate over time. Notice the steep left drop, representing infant mortality from factory defects. Once filtered, the machine enters reliable use, until dust and vibrations cause the failure rate to climb back up. Physical objects have a defined lifespan. The environment will always win in the end. Computer software is entirely different. Code is a purely logical construct. It has no physical mass. Because it doesn't physically exist, engineers expected software to follow this idealized curve. After initial bugs are fixed, the failure rate drops to 0 and stays there. Code doesn't rust or generate friction. Once sound, it should theoretically run flawlessly forever. Yet anyone who uses a computer knows this never actually happens. Apps crash, operating systems freeze, and programs break constantly. To keep older applications running, organizations maintain massive teams of developers. The global effort required to manage this aging, so-called legacy software absorbs billions of dollars, outpacing the creation of new software. This deterioration points to a failure mode unique to the digital world. The divergence between these two industries starts at the source. Hardware is manufactured, while software is exclusively engineered. When a physical gear fails early in its life, the original blueprint is fine. The failure is a slight misalignment introduced during the manufacturing process. Software has no physical assembly line. There is no manufacturing phase where a robot might drop a screw. That means every single software crash is an error in the original design itself. These design errors slip in when developers try to translate complex human requirements into strict, rigid machine instructions. When software breaks, we aren't hitting the limits of metal or plastic. We are hitting the limits of human cognitive capacity. This brings us to this actual failure curve. Instead of a flat line at 0, the graph is interrupted by sudden, violent spikes in failure rates. Forced changes trigger these violent, sudden spikes on the failure graph. Users demand a new feature. A third-party database updates its protocols. The operating system shifts. And every time that developers adjust the code to accommodate these demands, they trigger one of these spikes. We call these side effects. When developers alter the code, they inadvertently introduce new, unexpected errors. Over time, as these changes accumulate, the baseline failure rate climbs steadily higher. Code doesn't deteriorate from friction. It deteriorates because it buckles under the weight of its own continuous evolution. The problem compounding when engineers try to address these inevitable failures. When a physical machine breaks, a mechanic can grab a standardized, off-the-shelf spare part and drop it in. Software doesn't have spare parts. Because most systems are highly customized, there is no generic replacement component you can swap in to fix a broken line of code. To fix a bug, a developer has to dive back into the raw logic and rewrite it. That fix qualifies as a change, which introduces side effects, triggering a new spike in failure, which requires another fix. Software functions as an active information transforming process. Because continuous change is the natural state of software, it requires continuous, disciplined engineering to keep it from collapsing under the weight of its own immortality.